Good day, Calc students. Today we're going to talk about FTC2. That stands for the Fundamental Theorem of Calculus, Part 2. And you've already been through FTC1, which is telling us how to integrate a function from A to B. FTC2 is a little different than that. It's focusing on what's called an accumulation function. FTC2 is written this way. If f is a function, f is continuous on an interval, and the variable a is any point in that interval, then this relationship exists. The derivative with respect to x of the integral from a to x of f of t dt equals f of x. Now, if you're anything like me, that relationship as a standalone is semi-confusing. It probably doesn't make much sense from the beginning here. But as we look at some examples, this is going to become quite clear to you, and it's going to be a nice tool to have in our toolbox to arrive at answers quickly. It's a nice shortcut, in fact. But you might notice here initially that we're talking about two things in one statement, both a derivative and an integral, and you know those two things kind of undo each other. So that's going to be an important big picture concept here as we move forward. So know that both a derivative and an integral kind of undo each other. If you take a look at that integrand f of t dt, we're going to integrate it, then differentiate it. It makes a little sense perhaps that we land on f of x when the dust clears. Let's take a look further. I have this caution symbol for a reason. This upper limit of x. Here's a hint we're going to look at later. What is the derivative of that upper limit? What is the derivative of x? The derivative of x is just 1. The truth is, our final answer of f of x is indeed multiplied by 1. That's important when that upper limit becomes something more complicated than just the variable x. Stay tuned. So this is problem number 1. Let's evaluate the derivative of the integral from 0 to x of cosine t dt. The fundamental theorem of calculus, if you look at that, it tells us that the answer should be, again, we are differentiating and then integrating. Those two undo each other. The answer here should equal the cosine of x. What we're going to do is actually we're going to work from inside out. We're going to integrate cosine t and then evaluate it from 0 to x and then differentiate that answer to see what we get. Bear with us here. The verification works this way. We're going to differentiate. Let's see, what do you get when you integrate cosine t? When you integrate cosine t, you get sine t, and we're going to evaluate that from 0 to x. Again, we're working inside the square brackets. Well, this means I'm going to differentiate the sine of x minus the sine of 0. We simply put in the upper limit minus and then plug in the lower limit. All right? Now we're going to go ahead and differentiate that. Well, do you know what you get when you differentiate the sine of x? First of all, let's evaluate the sine of 0. The sine of 0 is just 0. Now let's differentiate. Well, I'm going to differentiate sine x. I'm going to differentiate 0. The derivative of sine x is just cosine x. The derivative of 0 is just 0. Check it out. When we verified this, the answer we got was cosine x. That's after we differentiated an integral. exactly what we expected to get, we did get. So the shortcut using FTC2, we thought we'd get cosine x. We did the work. We went a long way around the block. We did indeed get cosine x. Let's see if this pattern continues with a second problem. This is number 2. We want to evaluate the derivative of the integral from 3 to x of t squared dt. Alright, let's take a look. First of all, what should that equal if I use the shortcut for FTC2? Well, you said earlier that the derivative and the integral kind of undo each other. And you slap in that upper limit in place of the t. You should just get x squared when the dust clears. Alright, let's verify that. Let's take and differentiate the integral. Well, when you take the integral of t squared, what do? That's just a power function. Add 1 to the exponent and divide by the new exponent. Add 1 to 2, you get that 3, divided by the new exponent. Divided by 3, and we're going to evaluate this from 3 to x. So how do I evaluate that again? I'm working inside the square brackets. I put in the upper limit, minus, I put in the lower limit. Looks this way. Again, I'm still going to differentiate this after I sub in the upper and lower limits. There's the upper limit, x cubed over 3, minus, plug in the lower limit, 3 cubed over 3. That 3 cubed over 3, what's that? 3 cubed is 27 divided by 3 is 9 when the dust clears. So I'm going to differentiate x cubed over 3 minus 9. Well, we're pretty strong at differentiation. Let's differentiate using the power rule, x cubed over 3, and get 3x squared over 3. When I differentiate the constant 9, I just get 0. 3x squared over 3 is just equal to x squared. We thought were going to get x squared. Indeed, we did get x squared. Mr. Foster, why are we going through all this work if we know what the answer is going to be? Can't we just go directly to the answer? Stay tuned. Number 3. Let's evaluate the derivative with respect to x of the integral from pi to x squared of sine of t dt. Have you noticed that the lower limit with each example so far has been a constant? It needs to be a constant if you're going to use FTC2. It doesn't need to be 0. After all, when I plug that in and differentiate, when you differentiate that constant, you're going to get 0. Okay? So that lower limit has got to be a constant, but that constant does not have to be 0. Well, this one is a little curious. I notice the upper limit this time isn't just a normal x. It's x squared. Be careful. So this time I think it should equal the sine of x squared. But I'm going to be wrong. This is on purpose. Let's see. The wrench in our plans. Sine of x squared is going to be wrong. I left some room in front of sine of x squared for a reason there. Maybe you can already anticipate what's going to happen. But let's do this a long way so we can understand, have an understanding of exactly what's going to transpire when that upper limit is something other than just a simple x. Here comes our verification as we've done in the past. Our verification try. We're going to differentiate and we integrate immediately the sine of t. And I know that the integral of sine is negative cosine. We're going to evaluate that from pi to x squared. So I put in the lower limit first, minus, I put in the upper limit, first, minus, put in the lower limit second. Work should look like this. We're going to differentiate negative cosine x squared minus negative cosine pi. Again, a result of putting in the upper limit first, subtract the lower limit second. our next line of work. Still working and simplifying inside the parentheses. Subtracting a negative is the same as adding. And on the unit circle, if you contemplate the cosine of pi, the cosine of pi on the unit circle kicks out an output of -1. Okay, so at this point in the problem, we're going to differentiate negative cosine x squared. Then we're going to differentiate -1. You already know that the derivative of -1 is going to be 0. It's this first part I'm really concerned about. Do you know how to differentiate negative cosine x squared? That's going to require a little chain rule. You see that the inside function is x squared. And when you differentiate that inside function, you're going to get 2x. So as we move forward here, I know when I differentiate negative cosine x squared, what I'm going to get is 2x times the sine of x squared. That's not what I thought I was going to get. I thought I was just going to get the sine of x squared. But I have that tag at the beginning of a 2x. I need that tag at the beginning of 2x, meaning it's true to use FTC2. All you do is you take that upper limit and you substitute it in for the variable in the integrand. But you also must multiply by the derivative of that upper limit. Remember, when it was just x, the derivative of x was just 1. You didn't notice it. But now that the upper limit is a little more complex, it's x squared, notice, simply take an x squared and plug it in for t, get the sine of x squared, but then multiply it by the derivative of that upper limit, which is 2x. That is necessary. So in layman's terms here, how do I execute FTC2? Solve an FTC2 problem, which is taking the derivative of an integral, knowing that those two undo each other, by substituting the upper limit in for the variable t. And then remember the key here that you need to digest that other students will not. Then you must multiply by the derivative of that upper limit. So sub in the upper limit for t, then multiply by the derivative of the upper limit. That will give you your final answer. Well, I don't understand. Why don't I just do the problem like you've been doing the problem? I mean, I know it's going to take a little longer, but I can arrive at an answer that way. Well, oftentimes you won't get a function that you know how to take the integral of. Functions that we know how to take integrals of are known as elementary functions. Well, oftentimes you'll get a scenario where you're unable to take the integral of that function, but you can still use the shortcut for FTC2. Super valuable, super powerful. So you get a scenario where you're taking the derivative of an integral, take the upper limit, plug it in for t, multiply by the derivative of that upper limit, and you have a shortcut answer where you don't have to do all the work. Let's see if we can do this. I know a scenario like this. You take the derivative of the integral from 0 to x of cosine t dt. Simply plug in the upper limit, which is x, in for t, and then multiply it by the derivative of the upper limit, which is just 1. Done. Second scenario. the derivative of the integral from 3 to x of t squared dt. Take the upper limit, put it in for t. You get x squared. Don't forget to multiply by the derivative of the upper limit, which is just 1. Done. Our third scenario, the derivative of the integral from pi to x squared sine of t dt. Take that x squared, plug it in for t, you get sine x squared. Don't forget to multiply by the derivative of the upper limit, which is 2x. The shortcut of FTC2. You try one. What if we get the derivative of the integral from 2 to x cubed of cosine t cubed dt? Can you use FTC2 and arrive at the answer? Go ahead. I tell you what, you can't do this a long ways. Even the finest mathematician in America doesn't know what the integral of cosine t cubed is. But you know a great shortcut for arriving at an answer whenever you're asked to take the derivative of an integral. Simply take that upper limit and plug it in where you see a t. Be a little careful here. You're going to have to go x cubed x cubed is going to give you an x to the 9th power. And did you multiply that by the derivative of the upper limit? This is a multiplier of 3x squared. Be careful. A few words of caution here. FTC2 and FTC1 are they can be swapped depending on what textbook you're looking at and what website you're looking at. They're often switched depending on like the author's order of presentation of how they're kind of putting this picture together. So be a little careful here. FTC1 and FTC2 are often switched depending on the textbook or the website that you are using. So you get on Khan Academy or something and you type in FTC2, you might be looking at an explanation and going, man, that seems a lot like FTC1 to me. So just know that going in, that depending upon the textbook or the website that you are utilizing, FTC1 and FTC2 might be swapped up. Okay? So when you see problems today, remember all you're going to do is take the upper limit, put that in for the variable, and then multiply it by the derivative of that upper limit, and that's how you will arrive at final answers for problems that deal with FTC2. You should be sitting in butter. Hope this is clear. Good luck on your work in class and this evening. Calculus made easy. Over and out.